I love lights. I love making them, modding them, salvaging and repurposing them, and from night lights, reading lights, workbench lights, torch lights, decorative lights, to modding laptops from meeting lights. I have made so many of them, sometimes even as a gift. Heck, even this channel started with me making panel lights for shooting our videos. I wouldn't quite call them studio lights, but for what they're worth, they have served us really well for over 2 years now, and are still functional the exact same way as they were when I made them. But I think it's time for them to retire and for us to upgrade our studio lights. Come with me and I'll tell you exactly how I'm making my studio lights that you can't just buy off the shelf. Studio lights, like most other high-power LED lights, are actually pretty straightforward. They have structural components like the enclosure, mounting mechanism, and a thermal solution. Most often, these aren't distinguishably different parts. They also have the optical components, namely the LED chip, but also reflector, softbox, diffuser, filters, etc. But to use the light, you need its functional components, the power, logic, and the LED driver to give you the illumination you need it to. They can be as simple or as complex as you want them to be, depending on the features that you want. And last but not the least, the control components. May that be the knobs, sliders, remotes, or apps, which manages the functional components to bend to the user's will. Oftentimes, they are part of the light's enclosure itself, but can also be a separate unit when you need the control to be wireless. Now, for the light that I'm going to make, I have made a checklist for it. Aside from driving RGB channels and managing color temperatures, we also want the control scheme of our light to be multimodal and wireless, among other things. I'll explain them as we go, but first, let me show you what I mean by the color channels and control schemes with a basic demo. Alright, so now here we have pretty much all those components of an LED light in action. What I have done here is created a structure out of a broken laptop's back. The drivers are something that you can buy off the shelf. This is a consumer grade LED strip, RGB LED strip. I have connected it to a 12-volt power source and wired them together. Here I'm controlling red, green and blue from 3 different controller or driver, and if I turn this dimmer up or down, you can see their corresponding color channels are going up and down. This is just to demonstrate that all the different colors that we end up creating as part of our RGB light presets, those all are created from RGB, red, green and blue channels, just the same as our monitor pixels. And because all these things are pretty much off the shelf except for the structure, the part that you first need to focus on are the controller and the drivers. In this simple demo, the controller and the driver are packaged inside the same box and it's intuitive enough. But if we want the driver to be remotely controlled, then we have to decouple them. And of course, you can buy something like that off the shelf as well. In fact, you can just buy lights with those specific features as long as that's the main thing that you're looking for. But the moment you start stacking all those features and don't want to compromise one for the other, that's where it starts to become a problem. Because you see, if you were to just buy a studio light, it's a three-way tug of war between cost, availability, and the features. And the combination of features that we want, practically speaking, isn't up for sale. The only way they would be available without compromising its features, that is if a Hollywood studio commissioned them for a bespoke use with a blank check to make it happen. And even then, it will miss its mark here and there, but that's where being a maker has its advantages. Because I'm stupid enough to set an impossible goal, smart enough to make it happen anyway, and careless enough to openly share it with the world. My goal in this video isn't to make something overly complicated. My goal is to make something so simple and intuitive that it leaves you wondering, why isn't this the norm in the first place?
Now that you know that we are making Roshan not only because we want to, but also because we have to, let's focus on getting its most complicated part working first. And that's the driver.
So, to make the custom driver, I opened up EasyEDA and started designing one. The design is based around the Seed Studio Xiao ESP32C6 module as the brain of the operation, and I'll tell you more about it in a moment, but first, I need to put in the order before the Lunar New Year to avoid delays. From EasyEDA, it's super easy to order PCBs from JLC PCB, the sponsor of today's video. JLC PCB provides easy, affordable, and reliable PCB fabrication and assembly solutions, empowering millions of makers to develop electronic projects efficiently. From EasyEDA, run a designs rule check, and with one click, order from JLC PCB for just $2 for 5 prototype boards. EasyEDA takes care of all the busy works, generating Gerbers, bill of material, pick and place files, and uploading everything automatically. Just review your order, choose PCB color, thickness, or other advanced features if needed. JLC PCB also offers PCB assembly, sourcing, placing, and soldering components with professional precision, far better than DIY soldering. But if you prefer hands-on work, you can also order stencils for precise solder paste application. Beyond PCBs and assembly, JLC PCB also provides layout services, as well as 3D printing and CNC machining for your mechanical parts and enclosures. Check out JLC PCB and grab a $60 new customer coupon by signing up with our referral link.
Now, while our PCB is being manufactured and is on its way, let's check out our design.
Our driver module is based around an ESP32C6. More specifically, the Seed Studio Xiao form factor. It's super tiny and packed with features for rapid prototyping, most notably the USB-C connector and the boot and reset buttons for painless programming. It has many other features under its belt. If you haven't tried it out yet, you should. This module is in charge of taking the control requests wirelessly and then driving the individual LED channels through PWM or pulse width modulation. In simple terms, it switches the LEDs on and off very fast, about 1,000 times per second, and for how long or short duration they stay on an average per cycle determines how bright they appear to be. And that is happening for each of the LED channels individually. That's red, green, blue as the color channels, as well as the cold and warm white channels for color temperature control. Each of these channels are driven by these AO3400 N-channel or low-side MOSFETs through these gate resistors and pull-down resistors. The main power supply we are working with is nominally 12 volt because it has to power the LEDs, but our ESP32 module can't handle that much voltage. So this low dropout regulator is in charge of providing you with a 3.3 volt diode for such a device.
Now, if the design seems bare bone, that's intentional. This is the part 1 of our Roshan series of videos. And my goal is to first just remotely control PWMs for dimming LEDs by sending control signals over REST API to the driver that we are making. I know I'm keeping it light, but if you'd rather want me to go super deep into how I chose those individual parts, which trade-offs did I make, what are other viable options to consider, etc., then please come join us on our deep dive live streams.
Now, as you may have noticed, my board is a 2-layer board and mainly contains through-hole components. This is so that if I have been stupid in my design and made mistakes in my first iteration, it will be much easier for me to fix it while soldering without any jumpers or board wires, or worse, updating the design, sending another order and waiting for it to be shipped again.
The trade-off is that each of those factors make routing the board extra difficult, but it does save us from high latency iterations in favor of low latency iterations. So from a fail-first perspective, that makes it totally worth it. Now, all we need to do is just wait for the boards to arrive. Alright, so I got the components soldered into the board, and time for us to test if everything is alright and whether there's the magic smoke that comes out. Hope not. I'm going to first put the 12-volt power. Yeah, so the voltage is showing 12 volt. As you can see, the LDO is not hot and there is no capacitors that has blown out. So I'm going to put the module in. I have programmed the module with a simple blink sketch where each one of the channels that it has, like that is red, green, blue, and cold and warm white, each one of the channels are basically blinking at half a second interval, and I'm going to test that all of them are working or not. This will validate that all the channels that we have assigned, all the traces that we have assigned for the particular output drivers, they are all working. All right, that means it's time for us to write a firmware for it to run.
Nothing complicated, we just need to connect our ESP32C6 module to Wi-Fi, set up the LED controller channels with some specific defaults that we don't need to worry about too much as long as the dimming works. And for the dimming to work, we have to set up a web server which takes REST API requests and sets the LED brightness accordingly. Easy peasy lemon squeezy 300 lines of C++. And here's how it works. You got that? Let me do it again. There. You got it?
Now, you must be thinking, well, that's anticlimactic. Typing commands on a CLI for changing LED brightness?
And you would be right. Now, if you recall what we said in the beginning about the controller being multimodal and wireless, actually, that's just the tip of the iceberg. In its final form, we'll have a suite of apps, remotes, and dedicated decks as controllers, with different connectivity and protocols working under an unified abstraction layer as a hub. But if you also recall what we said in the beginning, this is just the part 1 of a multi-part project. We'll have to make this monster one organ at a time, and the controller will get its own dedicated video later. But in this video, our main focus is the driver. So for the time being, let's make a web app for controlling the LEDs as a proof of concept. It will give us near identical user experience as to a dedicated controller, but at a fraction of commitment to validate our effort. Now let's put everything together and see how it works.
This project took an unholy amount of planning, effort, and time. I hope you like this part 1 of Russian. There is more to come, of course, and I hope to share my journey all the way to the completion. You can now follow us on Instagram and X for behind the scenes and early bird updates on the projects that I'm working on. And on Sundays, there's the deep dive live stream. I hope to see you all there. Thanks for watching and break it till you make it.